You know how a lot of times twins will have this really crazy connection to each other? Well, I knew these twins, Emily and Abby, and they were separated at birth, but they found each other later in life and found out that they used the same brand of toothpaste. They loved the same types of foods, type of music, movies. They had the same mannerisms, but they even grew up in different states. Emily grew up in California and Abby grew up in Texas. They had different families, obviously, so many different aspects of their upbringing, but they ended up being so similar. The only thing that they found out that was really different about them is that anytime that they needed to go up a flight of stairs, that Emily would always take the stairs and Abby would always take an elevator. So I guess you could just say that they were raised differently. So today we are returning to something that we have done before because we have new skills and knowledge that we can add to it. So limits at infinity, hopefully we're remembering if I'm looking for a limit as x is going to a positive infinity or a negative infinity, the first thing that I look for is, does this function have a horizontal asymptote? Because if it has a horizontal asymptote, then as x goes to infinity, my y values will eventually be bounded to that horizontal asymptote. They'll get really close to it. If it doesn't have a horizontal asymptote, then I have this whole aspect of plugging in larger and larger numbers. It's kind of a trial and error, the table look of a limit to see what we think it is approaching. So we're going to look at a different way that we could see that. So remembering what we have done before, the very first thing that I will do, and that part hasn't changed, to see if this has a horizontal asymptote. So using that Bobo Boat needs DC. And definitely for this situation, it is an eats DC. And so we would say, okay, the horizontal asymptote is at 4, so that must be my limit. As my x approaches infinity, my y values are going to get closer and closer to that horizontal asymptote at 4. Okay, so what we are going to add in today, which can be helpful for limits at infinity, but also we can use it for other things as well. This is the fancy L'Hopital's rule. L'Hopital's rule has conditions that we have to have an indeterminate form whenever we're initially trying to evaluate the limit. So if I plug in whatever I'm approaching and I get 0 over 0, which happens a lot for us, or like in my first one, if I tried to plug in infinity in the numerator, I'm really getting infinity because if I plug in larger and larger numbers, they're going to go to infinity. My denominator is also going to infinity, so that would be an indeterminate form as well of infinity over infinity, but it doesn't matter the signs as long as it's going to one or the other. Both of these are indeterminate forms. So L'Hopital's rule says if I am plugging in that value and I get an indeterminate form, then I am allowed to say that the limit as x approaches whatever that a value is of f of x over g of x, and yes, this is always going to happen with a fraction because notice both of our indeterminate forms are fractions. It tells me that I am allowed to say that that limit is equal to the limit as x approaches a, so that part doesn't change, of the derivative of f prime, over the derivative of g. Okay, so this is kind of magical. This is not the quotient rule. Quotient rule is a lot more complicated. We wish this was a quotient rule. Remember, the quotient rule tells us we've got the derivative of f, so f prime times g minus g prime times f all over g squared. So it's a lot more complicated. This is not the quotient rule. We're not taking the derivative straight out. This is only with limits, and in this condition, we are allowed to say that this limit is going to be equal to this limit. And that's anytime we get an indeterminate form. So we could go back to this guy, and I know some of us have a harder time remembering our Algebra 2 things. So if we got to this and we said, oh, I don't remember how to find horizontal asymptotes, or maybe you don't even remember that you were supposed to be finding a horizontal asymptote. Well, when we plug in an infinity to the x in the top, I get this goes to infinity and this goes to infinity. So that is an indeterminate form, which means that this limit, by L'Hopital's rule, is equal to the derivative in the numerator, so an 8x, over the derivative of the denominator. And it doesn't always work exactly this way, but this ends up being a whole number, so it does. My x's end up canceling, and then I don't actually have to evaluate the limit, really. It evaluates it for me, that 8 divided by 2 is 4. We could even, well, we'll see some other examples with that, but things where we would have factored before and then canceled, we can use L'Hopital's rule for that as well. Sometimes that's going to be faster, sometimes not, kind of just depends. But let's look at some other examples. So we've got example 1 here, and this one is not a limit as x goes to infinity. I know that's the title of today, but it really should be like L'Hopital's rule and awesome stuff. So limit as x approaches 0, we're first trying to plug in 0, and we would get sine of 0 is 0, and then over 0. So we have that indeterminate form. So I maybe have other strategies. This is one that we have memorized before, and so maybe we can figure it out that way. But by L'Hopital's rule, we are allowed to say that this is equal to the limit as x approaches infinity, or sorry, of x approaches 0 of the derivative of sine, so cosine, over the derivative of x, which is 1. So now I'm able to evaluate. I can plug in my cosine of 0 and I get out 1. So that's another way that we can look at, this was a trig derivative or trig limit that we were memorizing at some point. So another way to approach it is using L'Hopital's rule, it equals 1. It's also helpful if we're looking at a limit as x approaches infinity and we get a boson. So in this case, we've got bigger on top, so it is a boson. And if I plug in infinity into my numerator, it's going off to infinity. My denominator is going off to infinity as well. So really right there, we've kind of got it. It's going to be a positive infinity. But sometimes they're a little bit more confusing. Maybe, I don't know, maybe this coefficient seems like it's going to change everything if it's like 2000 in the middle, or I don't know, we can get kind of tripped up in what signs are going to happen. So since I know this is going off to infinity, my denominator is going off to infinity, I can go ahead and look at, using L'Hopital's rule, my derivative of the top. So we've got a 150 x squared minus 40. And every time we take the derivative, we get one less power, and so it becomes less difficult for us to analyze it. So maybe at this point we're saying, oh, this is easier to tell that this number in the numerator is going to keep getting larger and larger because that minus 40 is not going to affect it a whole lot, and so is the one in my denominator. But even here, if I plugged it into the numerator, I get positive infinity, denominator is positive infinity, so I can really go one more time. As long as I'm getting that indeterminate form, I'm allowed to use L'Hopital's rule. So one more time, I get 300x in the numerator, I get a 40 in the denominator. So now I really know that if I'm plugging in larger and larger numbers, my overall limit is going to infinity. So sometimes it helps just to solidify what we already thought was going to happen. I can justify it to myself that, oh yeah, this is definitely going to go to infinity. Okay, so why don't you go ahead and pause and try a couple of these. See if you can use L'Hopital's rule. Now they don't all require them, so require L'Hopital's rule. But pause it for a second and try these for yourself. So for the first one, we should be using Bobo Boat Needs DC, that we've got a bigger on bottom, so using L'Hopital's rule is not necessary. You could if you wanted to, but eventually you're going to get that the denominator is going to infinity and the numerator is a constant. You end up with, let's see, you got an 8x, so you'll end up with 8 in the top and an x in the bottom. So while the denominator is going to infinity still, the numerator is just a number, so it is actually going to infinity, which is the horizontal asymptote. For 4 and 5, they both are botons, they're bigger on top. We can use that L'Hopital's rule. They're actually the exact same function, just looking at a positive infinity versus a negative infinity. I definitely think L'Hopital's rule is really helpful for that negative infinity, because sometimes, I don't know about you guys, but it's a little bit more difficult for me to think through plugging in larger negative numbers than it is larger positive numbers. So here you end up with this 8x over 1 both times, knowing that if I plug in larger positive numbers, it goes off to a positive infinity, but if I'm plugging in -10, -20, -30, it's going to go off to a negative infinity. So we could even use L'Hopital's rule for things that we've simplified in the past. Just a few examples of that. Not always the easiest, it just depends on what it is. So for this guy, this was a pretty easy limit before, where we plug in 3 to begin with, we get that 0 over 0, and so we're just factoring the top, and then we can cancel and then plug in our 3. So with L'Hopital's rule, again, we're saying that we've got 0 over 0, that's what allows us to use it. But when we take the derivative of the numerator, we get a 2x, the derivative of my denominator, goodness, is 1, and then I can plug in my 3 and I get 6. So a pretty fast route. And either way, I don't know that either of those, and sometimes we don't show all of our steps there, so I don't know that either of those are any faster. Now this guy, if we are good with our derivatives, and some of us need some work there, if we're good with our derivatives, then I definitely think L'Hopital's rule is faster. So before, when we had something like this, we would multiply by the conjugate, and then we had this pattern where the numerator always ended up being what the original denominator was. We could cancel them, and then we were allowed to, and I stopped writing my limit, and my apologies. I definitely need a limit written right there, because this doesn't make sense that that would follow that. Okay, but finally, we're finding the limit by plugging in 2. So at the beginning, again, this is one where if I plugged in 2, I get 0 over 0, so that's what allows me to use L'Hopital's rule. Now, this one is a more challenging type of taking a derivative. I've got that radical in there, so really that x plus 7 to the 1/2. So when I use the power rule, I have a 1/2 x plus 7 to the negative 1/2. And then I would have to multiply by the derivative of the inside, but it's just 1. The derivative of -3 is 0, and then the derivative of my x minus 2 is 1, so I don't really have to worry about that either. So at this point, I can actually plug in my 2. I'm going to go ahead and simplify, at least moving the square root of x plus 7 to the denominator. No, now I don't need to write it. Now I can plug in my 2, and I get the square root of 9, which is 3, and we still end up with 1/6. Just like I did up here. Okay, so L'Hopital's rule, pretty fancy stuff. The last thing that I want to talk about today are infinite limits that involve trig functions. So we've seen some trig limits before. Really, we've only dealt with ones that either we had memorized, those limits as x approached infinity, or as x approached 0. But other than that, maybe we've plugged in specific values. So like we could find the limit as x approaches pi over 2 and plug it in and just evaluate. But we haven't seen any trig limits that x approaches infinity. So something interesting happens here. If I am approaching infinity for cosine of a value, those values, think about what the function cosine looks like. It just goes up and down. It oscillates. Not as crazy as some oscillating things that we've seen, but it is going to go in between two values. So there are other cases where it could be combined with something else that this is not true, but since this goes back and forth in between values forever, this does not exist. The same would be true for sine. It's still gonna go up and down forever. The same would be true for tangent even. It's got a bunch of asymptotes in it, but it just starts at negative infinity and goes to positive infinity. It keeps doing that over and over. So it never actually lands anywhere. Now for things like 7 and 8, so this is a little bit different. We have talked about the squeeze theorem before, but here's the squeeze theorem in action and really what we mostly use it for. If I'm trying to find the limit as x goes to infinity here, I know that my cosine function is going up and down forever, but 3x is not. So what we're going to do is look at the two functions that this would be stuck in between. It would be stuck in between a function where cosine is at its least, So plugging in, there are tons of different angles I could plug in, but the least value I would get there is a -1. And then it's going to be stuck in between. So in between we've got our 3x plus cosine x. So it could be equal to that at times, but it's always greater than or equal to. On the other end, the greatest that cosine could be is 1. Okay, so we've got this function that's stuck in between this 3x minus 1 and 3x plus 1. It's always in between those two things. Okay, so if we're trying to decide what the limit is as x approaches infinity, I can look at the limit of both of these values. So my limit as x approaches infinity of 3x minus 1, which it would go off to infinity, it's just a line. And then also my 3x plus 1, it goes off to infinity. So if my 3x plus cosine is stuck in between these two values, their limits, it tells me that the limit as x approaches infinity of this 3x plus cosine by the squeeze theorem has to be a positive infinity because it is stuck in between these two functions always, so it's got to be infinity. Now, looking at this with an actual value, I think makes a little bit more sense. 8 is very similar to that, where cosine is going to oscillate up and down, but these parts will not. So I could go ahead and look at the lowest end would be a 3x minus 1 over x squared. The highest end would be a 3x plus 1. And for both of these functions, if I'm looking at the limit as x approaches infinity, I've got a bobo here and a bobo there. So I've got bigger on bottom, my y equals 0 is my horizontal asymptote, so that is where it will be stuck. Same thing for 3x plus 1 over x squared, it is 0 as well. So if my function is always stuck in between, or if I'm taking the limit in between 0 and 0, that means that my limit has to be 0. You could also use L'Hopital's rule here. I might try that and see if you're getting the same thing. Okay. The last one. The last one's a little bit different. For this one, I have an extra element, I guess, because there's a 3 in there. But as I plug in infinity, I don't have this sine function just like oscillating, because as x goes to infinity, it's going to make this angle go to 0, because that x is getting larger and larger, and as our denominator gets larger, the overall angle is going to 0. So this is actually the same as the limit, and you can take these separately because the limit as x approaches infinity of this by Bobo Bowden, that would be a horizontal asymptote at 0. So this is the same as the sine of 0, which is 0. Okay. So just some things to think about with the trig functions and limits as x approaches infinity. Thinking about the fact that they oscillate, and sometimes if we're looking at just cosine x or tangent x or sine x, then that part of it is going to go up and down, and so we might have to consider the least end and the greatest end and see if they do converge, if they end up being the same limit. Or we might have a situation like this where part of that limits to something, and then it allows us to evaluate the trig function.